Now that we have the governing equation of motion for our transverse beam, granted under some limitations that we have this constant cross-sectional area, constant material, and we have free vibrations, we are interested in finding W of xt. Now, in this course, we are not going to go and find that full solution for W of xt. It is going to be more complicated, certainly, than what we saw for the axial problems, because we have this fourth order equation rather than just having a second order equation in space. So we're going to go through some of the steps we would take, but not going to go through and find the full solution. What we see based on the PDE is that once again, we have that W is separable. In our PDE, we have no mixed derivatives of W. We have strictly a spatial derivative, a fourth spatial derivative, and then strictly a second time derivative on W, and there's no mixing them. So that means that W we can write as the product of two 1 degree of freedom variables. Some big W that is a function of only space, and some function T, big T, that's only a function of time. And if we take this and we substitute it back into our governing PDE, then we can get the expressions that look like this, where the first term is affecting only the W, and the second term is affecting only the T term. Now, with a little bit of hand waving like we saw in the axial problems, we're going to be able to push the time to the right-hand side where it's currently 0, and we're going to get that we have a fourth derivative of W is equal to a second derivative of T. However, W is a function of only space, and big T is a function of only time. So for convenience, because we have a differential equation equal to another differential equation, then because they are of different variables, we can say that they must be constants for them to be equal to each other. And we're going to call that constant omega squared. So again, you can look at more detail back in your ordinary differential equations or partial differential equations class for this. But because we are differentiating with respect to two different variables and they're equal, we can set it to some constant. And for convenience, we call it omega squared because this will become our natural frequency later, as we're going to be seeing. So we now have two ODEs because we have this separable equation. So we can take this first term and make it equal to 0. Where I'm pulling the W term, I'm pulling the omega squared actually to the left-hand side, and I have a beta, which we'll see in a second what that looks like. And a second ODE, where again I can pull this negative to the other side, and now I have this derivative of T, I can multiply through by T, and that's equal to 0. So I just rearranged this equation equal to omega squared and this term equal to omega squared as two ODEs. And here I am defining a term beta, where beta to the fourth power is omega squared over that c squared that we saw earlier, which is dependent on E, I, rho, and A. So instead of having omega squared, I've rewritten this term. I have a beta squared for my W equation, and we'll see why working with beta is going to make sense as we track down the natural frequencies of our transverse beams and its eigenfunction. So the beta to the fourth is just a construct mathematically that's going to be useful to us. So as with the axial problems, what we are going to be interested in doing is solving these two ODEs. We're going to start with W typically because, like with the axial problems, we're going to be able to apply boundary conditions, and we're going to be able to find natural frequencies and mode shapes, or the eigenfunction. Then we can apply initial conditions and work on the T equation. Again, in this course, we're actually not going to go that far with the analytic solution, but that's where we would be headed if we wanted to find the full analytic solution for transverse beam problems. So let's look at W. Notice this is a fourth order differential equation. To this point, we've really only ever seen second order differential equations, ODEs, and tried to solve them. But we have here just this fourth derivative of W and then a W term. In this equation, there's no third derivative, second, or first derivative, and that's going to make the solution look a little bit simpler than it really could be if we had all of these middle derivatives of our terms as well. So where we can start with this is that we can have an assumed solution for our w of x, that fourth order ordinary differential equation. So we will write our assumed solution for w in this form with 4 terms to it. So it's going to have a cosine term, a sine term, a cosh term, and a sinh term, where the cosh is going to be hyperbolic cosine and the sinh is hyperbolic sine. So 4 terms and 4 amplitudes, 4 unknown constants, C1, 2, 3, 4, that we are going to be able to solve, or at least work through, using our boundary conditions. And we're going to be seeing that the natural frequency, in the end, when we work through this a little bit, but the natural frequencies are going to be related to these betas that we find. So the beta squared times c is going to give us our natural frequencies. Once we get through our examples, this will start to make more sense. But as we go through finding natural frequencies and eventually the mode shapes, we are going to be applying 4 boundary conditions to solve the constants for this fourth order ordinary differential equation. And this is again on w, which is going to be our position and its derivatives as well. Its spatial derivatives. So during this step, we need to identify our boundary conditions. Where possible, we are going to know a location on the beam with 0 displacement, and we are only looking at homogeneous boundary conditions for this course. So all of these boundary conditions are going to equal 0. So is there a location on the beam where the displacement, the vertical displacement, is always going to be 0? This could happen at places like a wall or a pin connection where it cannot translate vertically. We can also have boundary conditions on the slope. Are there places we know the slope is 0? This could occur somewhere like a wall, where the slope at the wall must be horizontal, then it can start to have a non-zero slope. We could have other sorts of conditions in there that would hold the slope at 0 without necessarily holding the position at 0, and some sort of more exotic connectors that could do that. We could also know what the internal bending moment is when it's 0. So for example, on a free end, we are going to have 0 internal bending moment. Again, these are spatial derivatives of w, so that's why we are going to have the position, the slope, its relationship to the internal bending moment. When it's a homogeneous boundary condition, meaning it's equal to 0, we can simply say that the second derivative is equal to 0. If we have non-homogeneous boundary conditions, then we're going to have to involve e and I as well. But for here, with homogeneous boundary conditions, second derivative of w set to equal to 0. And are there places we know the internal shear force is here 0, but for other non-homogeneous boundary conditions, a known value? For the shear force, once again, if we have a free end, then we know the internal shear force at that location is going to be set to 0. So 4 total boundary conditions we're going to have among these 4 types of boundary conditions. Now, we don't have to have necessarily a w prime, w double prime, w triple prime. We can mix and match them because there might be some places where we know w is 0, some places where we know that the internal shear force or the bending moment is 0. But there'll be a total of 4 boundary conditions if we have a statically determinate beam that we're working with. When we get into using FEA, we're going to be able to handle non-statically determinate beams because we're going to get enough equations to be able to solve those. And as a quick aside, we are introducing this term, this hyperbolic cosine and this hyperbolic sine. So just as a quick review for how do hyperbolic trig functions work, well, they are defined based on exponentials. So e raised to, in this case, this x power. So the sinh is the difference between e to the x and e to the negative x divided by 2. And cosh, or hyperbolic cosine, is their sum divided by 2. And one thing that we want to remember as we go through, we're going to be using derivatives of our trig functions and our hyperbolic functions. Trig functions, we know how the derivatives work. We work with those often. But recall that hyperbolic trig functions are going to work differently. For hyperbolic trig functions, their derivatives are always positive. They do not change sign as we differentiate over and over again. So back to working with these boundary conditions. We're going to be working with them differently than we did for the axial problems. In the axial problems, there were only two boundary conditions, and what we saw was, at least when they were homogeneous, one of our terms in the assumed solution dropped out, and we had one term left, and then we were basically just taking an inverse sine or an inverse cosine, and we were able to find our natural frequencies. Things get a lot more complicated when we have these fourth order equations. Again, 4 boundary conditions, 4 of these unknown constants, C1, 2, 3, 4. We're going to use a different technique in order to find our natural frequencies. And in fact, we could have used this technique also for the axial problems when we had only a second order ordinary differential equation, but it's a little bit of overkill typically for a second order, but for a fourth order, it's going to be kind of required. So what we're going to do is we're going to write out our 4 equations from our boundary conditions. And again, because this is only going to be good for homogeneous ones, we're going to be able to write them, and the right-hand side is going to then be 0 for each of them. I'm going to take those 4 scalar boundary condition equations and rewrite them in matrix form. So A, we're going to see, is going to consist of sines and cosines and coshes and sinh terms, and I'm going to pull out the C1, 2, 3, 4 as its own vector. And then the right-hand side is going to be the 0 vector due to homogeneous boundary conditions. A similar idea, or really the same idea we're just going to apply it a different way, that we saw for axial was one solution that makes this true is that C itself is the 0 vector. But like with axial problems, that's going to give us a trivial solution, and it's going to say, therefore, that W is 0. Well, that can't be the case if we give it an initial condition. There's no way that W can be identically 0. Therefore, we don't want C to be the 0 vector. So what must be true is that if C is not the 0 vector, it must be true that the determinant of A must be 0. Again, I won't get into the math background on this, but we did see this before when working with ordinary differential equations. We saw this type of thing where we needed to take the determinant of a matrix and force it to be equal to 0 so that we did not get trivial solutions. When we take the determinant of this A, this 4x4 matrix, we are going to get a scalar equation equal to 0, and it's going to have beta in it. Like we saw with the axial problems, we are going to find the betas. In the axial ones, it was directly the omegas. Here, we're going to start with the beta values that make that expression true, and therefore, the betas that make the determinant of A 0. And there's going to be an infinite number of these betas that make the determinant of A 0, and each of these betas is then going to relate to a natural frequency of our transverse beam. So what we're going to do is we're going to be finding these beta values. Typically, we are going to need to solve them numerically because it's not going to be a nice periodic solution like we saw with the axial problems. So we're going to get a list of betas that we're going to solve using a root solver, probably in MATLAB or some other software. And once we have our beta values, we're going to be able to square them, multiply it by the C, and that is going to then give us the natural frequencies of our beam. And that's for analytic solutions where we will stop for this course. We're going to be interested in finding those natural frequencies for the beam, and we're going to have a lot of different combinations of possible boundary conditions, unlike the axial ones where there was really only 4 ways or 3 ways that we could put boundary conditions on an axial beam. Here we'll have a lot more combinations, meaning that the natural frequencies we find based on those boundary conditions are going to look a lot different from each other, even for the same beam, depending on how it's affixed to its supports. Is it fixed? Is it pinned? Is it free? And we can have different sorts of combinations of those.